Okay, so let's look at this 3D state of stress. So I want to know the state of stress if I cut it at plane AA, and in particular on that plane, I'm looking at point A on that plane. All right, so this is a 3D stress problem. At that cut, I can have three forces and three moments that each create stresses. So let me find those three forces and three moments. I'm going to come over here and redraw this. But here's my cut right there. There's my cut. And so I like to, in 3D, I like to draw my fx as if it's in the positive x, my fy. So these are my internal fx, fy, fz at the cut. These internal forces are what we get when we cut it open, when we open it up and we see those internal forces on that cut, on that plane. And they really counteract the external forces. And actually, let me, before I forget those, I still have this 1500 Newton force, still have this 1000 Newton force. Okay, so at the cut, I've got the three internal forces, but I also have the three internal moments. So let me draw, I'm going to do a double arrow, MZ, a double arrow, MX, a double arrow, MY, but you know that the direction of the moment is really the axis that the moment is rotating about, right? Remember, for 2D problems, all of our moments were in the K direction because clockwise and counterclockwise on a 2D sheet of paper would mean it's rotating about the z-axis, out of the page or into the page. So using the right-hand rule and curling my four fingers in the direction of the moment, the direction of the rotation, my thumb is the the axis that the moment is rotating about. So using the right-hand rule, let's think about this my fingers, my four fingers would be curled in that green arrow, right? In my right hand, my three fingers would be curled in that green area, and so my thumb is pointed in the X direction. Here, the MZ, let me do that at the moment. MZ, my three fingers are curled that way, my thumb is pointed up. MY, my four fingers are curled that way, my thumb is pointed in the Y direction. All right, we need to really be able to understand those moments, their directions. Okay, so let's solve for these three internal forces and three internal moments. It's really six unknowns, but we have six equations. We can sum the forces in X equals 0, sum the forces in Y equals 0, sum the forces in Z equals 0. We can also sum the moments about the X-axis equals 0. The sum of the moments about the Y equals 0. The sum of the moments about the Z equals 0. And so I have my internal Fx in the positive X direction, my internal Fy I drew that in the positive Y direction, my internal Fz, I drew those in the positive axes, and my internal Mx, My, Mz. All right, so those are my internal ones, but then all of the external ones are going to sum to 0. The internal plus external sum to 0. What do I have in the X direction? Let's see, I've got that 1500, but it's in the negative X direction. And I've got the 1000, that is in the positive Y direction. Whoops, positive Y direction. And those are the only forces I have. So I guess my force equations are done. I can sum those equal to 0. And what would I get? Fx, be careful, sum them equal to 0. And so the math would come out to be positive 1500. Fy, negative 1000. Fz, 0. All right, so maybe I shouldn't box that in. That's not my final answer, but that's a very important part of your answer, right? Getting that the internal forces are 1500 in the X, negative 1000 in the Y, and 0 in the Z. Now, I do that by summing the forces equal to 0. You could also just kind of ask yourself, okay, what do I need internally to counteract the external forces? Right? This is in static equilibrium. It's going to add up to 0, and so you can think about them adding to 0, or you can think about them just counteracting the external. The internal ones counteract the external ones. Does it make sense that we need a positive 1500, negative 1000 in the Z, a 0 in the Z, sorry? Okay, so this is my process. You might could jump straight to that, the more comfortable you are with these. All right, now the moments. I don't think you're going to be able to jump straight to, okay, what are the internal moments that I need? I think you really need to sum the moments in x equals 0, sum the moments in y equals 0, sum the moments in z equals 0. Okay, the way I like to think about it is every force can create two moments. Every force that is fully in one direction can create two moments in the other two directions, depending on how it is offset from the cut. All right, so we are looking at what type of moment will this 1500 Newton force create about the cut. There might be two. Which one do you see first? The one that I see first is if I'm going to be pushing this way right here on this arm, I'm going to create this rotation about the z-axis. See that? If I am got a force of 1500 newtons and a moment arm of 400, that would create a rotation in the z-axis. So I'm going to come down to my z equation, and I'm going to say, okay, 1500 newtons acting 400 millimeters away. Positive or negative z? If it's this way, if this is my arrow, you know, what type of rotation does this cause? Use your right hand, curl it about z. My thumb is pointed in the positive z, so that would be a positive moment. Let's double check that, and we did this a long time ago, didn't we? Second week of class or something. So it's been a while. I got to review, got to visualize these moments. This 1500 is in the x direction, and that moment arm is in the y direction. So it makes sense that we create a z moment, right? An x force with a y moment arm would create a z moment. Remember that the moment is perpendicular to both the force and the moment arm. So that's a good way to double check right there. Now the positive or negative, I just visualize. You just have to visualize it. Now if you really want to, maybe someone will do this, maybe I'll do this, I don't know. There's a formula for whether this would be a negative x with a positive y moment arm. Would that create a positive or negative z? And it really goes back to the cross product. Moment is r cross f, right? It's not f cross r, is it? Y'all double check me on this, right? R cross f. And so you could really go back to like doing a cross product of the r cross with the f. I don't know. I just can visualize, and I hope you can visualize, right, that this would create a positive, right-hand rule positive rotation about the z-axis. Okay, but it could create another moment, it could create another rotation, depending on how it is offset. Do you see that it is also offset? It's 200 millimeters above the cut. It's 200 millimeters above the cut. And so if I am pushing with some force 200 millimeters above the cut, it can curl down here and it can rotate in the about the y-axis. Rotate about the y-axis. So 1500, I'll do this in pink. 1500 with a 200 millimeter moment arm would create a y rotation. This is in the x direction. This 200 is in the z. So yeah, it makes sense that it would be a y moment. X force with a z moment arm would create a y moment. Positive or negative? All right, that rotation that I just drew, circling around. If I'm going this way, whoops. If I'm going this way, this way, this way, this way. If I'm rotating about here to here to here to here, using my right hand, curling my fingers, my thumb is pointed this way in the negative y. So 1500 newtons times 200 millimeters in the negative y moment. All right, can you visualize that? All right, and so those are the two moments that my 1500 Newton force could create. All right, how about this 1000 Newton force? How about this 1000 Newton force right here. I'll draw it in blue. 1,000 is 200 millimeters above, and so it would kind of bend down this way. It would bend down this way about the x-axis. 1,000 newtons, 200 millimeters. The force is in the y, the moment arm is in the z. So yeah, an x moment, positive or negative. Bend your four fingers, curl them around. My thumb is pointed in back this way, the negative x direction. Okay. Now that is the only moment that 1,000 Newton force would create. It is in the y direction. So this y displacement doesn't matter. This y is not a moment. The moment arm and the force cannot not be in the same direction, right? It doesn't really matter that it was 400 millimeters over this way. Let's see. It's a y direction that has a z moment arm. It could have had an x. So if this 1,000 Newton force, was back here behind the YZ plane or in front of the YZ plane, then it could have created a Z moment, but it isn't. It is right on. There's no moment arm in the X direction, so that force only creates one moment. Okay, so there we go. Those were all the forces creating all the moments that we could find. Set these equal to 0, and we would get mx, my, mz. I've got mx, 200,000 Newton millimeters. My, 300,000 Newton millimeters. Mz, negative 600,000 Newton millimeters. Box those in because it's so important. All right, are you following me there? That might take some review, some getting used to. But these are the internal forces. These are the internal moments at the cut. Okay, so now, each of those forces and each of those moments can create a different stress. Remember, go back to this page. We've got 6 different forces and moments creating 6 different types of stresses. I like to start with the axial, the one that is perpendicular to the cut, right? The one that is perpendicular to the cut. This one right here and this one right here, these are my axial. Z is my axial direction, right? And Fz, the axial force, would be the normal force, would be the normal stress N over A. Of course, it's 0. This one, we don't have to worry about that. But this one would be N over A. So then the others would be the VQ over IT. The shear stress, VQ over IT. All right? Now the moment. My axial moment is my torsional moment. It's the twisting moment. This would be the tau is TR over J. Whereas the others would be the bending moments, my over I, my over I. So I like to, just remind myself, identify, all right, what type of stress does each of them cause? All right, so now, I like to do this very methodically. Now let me start with this Fx of 1,500 newtons. It could cause... And so I say could, it might be 0 depending on the point that we're looking at. Could cause VQ over IT. The V would be 1,500, but the Q we'll talk about. All right, so I have an internal 1,500 Newton force in the positive X direction. Internal 1,500 Newton force right here. 1,500 newtons in the X direction. It creates a shear. So there's point A that I'm looking at. It creates a shear stress distribution that would look like this. So first of all, where's the neutral axis? The neutral axis is perpendicular to the shear force. So let's remember about this. The neutral axis for shear stress is perpendicular to V. And it would be largest if we were looking at a point on the neutral axis then that would be the largest. I would do VQ over IT. The Q would be Y prime A prime, and A prime would be, this, that would be A prime. But we're not looking at a point here or here or here or here, are we? We are looking at a point right here on this leading edge. And I know that for shear stress, on the very leading edge, right where it starts, right where it ends, that force, I think about that force as kind of beginning on this leading edge, ending on the trailing edge. It is zero. It is zero right here. If you really wanted to think about this, you would do the V. The Q is Y prime A prime, and that A prime, which is the area away from the neutral axis. If you're already out here on the edge, there's nothing away from the neutral axis anymore. That A prime is zero. All right, so this is zero because of point A, because of the point, right? It does have a V of 1500, but at point A, the shear stress is zero. All right, let's look at Fy. Fy negative 1000. It's a shear. It could be VQ over IT. Let me erase this because I have a new neutral axis. I've got a new force that I'm looking at. Don't reuse any of that. All right, so now I have a force in the negative y direction of 1000 newtons. What would that look like? I've got a force right here, of 1000 newtons right there. Where's my neutral axis? Neutral axis is right here. Shear VQ over IT would be largest at a maximum. It would be 0 right here and right here. And so point A is on the neutral axis, and it's going to be one of the larger points of shear due to that 1000 Newton force. So let's do the VQ over IT. So this would be V, 1000 newtons. Q, all right, Q is Y prime A prime. Q is Y prime A prime. Let me redraw this. 1000 newtons. Q is Y bar prime A prime. A prime, I'll start with A prime because it's easiest. It's the area, here's the neutral axis. It's the area away from the neutral axis of the point I'm interested in. That right there would be A prime. That right there would be A prime. Let me go ahead and do that. What's that area? The radius is of 20. The area would be half of pi r squared. All right. And then the Y bar prime is the distance from the neutral axis to the centroid of A prime. So that distance right there from here to there, that length right there, look on your formula sheet. The centroid of a half circle, the location of its centroid is 4r over 3 pi. And so that is that green line, 4r over 3 pi. This would be 4r over 3 pi right there. That was the Q. That was a tough one, but not too bad. All right, so that's the V, the Q. The I would be the I about the neutral axis. On that formula sheet, look at a circle. What is the I for this circular shape? 1/4 pi r to the 4th. All right. And then what is the thickness at the point that I'm interested in? The thickness right here, is going to be perpendicular to this V. All right, this V is right here. So the thickness would be this distance right here, the diameter. The thickness would be the diameter, 40 millimeters. I think everything was in millimeters. So I'm left with newtons over millimeters squared, which is MPa. This would be 1.061 MPa. That would be a tau. Specify whether it's a tau or a sigma. This is a tau. This is a shear stress. And let's say what direction this is in. Let's specify what direction this is in. Well, whatever direction the force was in, that's the direction all of these shear arrows are going to be in. No matter where I am, that force of negative 1,000 or 1,000 in the negative y direction, this shear stress is in the negative y direction. All right, I'm going to specify that because I might want to combine this with some other shear stresses that I've calculated. All right, might want to combine that with some other ones. I need to make sure they're the same type of stress in the same direction.